Hello and welcome to the another episode on tips and workflow. In this week's workflow video, I'm going to discuss on model requirement for the flow analysis. This is from the popular demand for the new users and probably a refresh for the existing users. I want to keep this clip or video short, so let's get started. So in terminology, we call as a mesh. So what is the need for the mesh is to represent the geometry into the subdomains or in a smaller element form. That's what we call as a mesh. Now in for the Moldflow or Autodesk Moldflow, we call this terminology into three types of elements. That's a beam element, we also call it a 1D element, triangular element, also called as a shell elements, and tetrahedral elements, that is the four noded element. Mesh types used in Moldflow: midplane, dual domain, and tetrahedral. A 10-second glance on it. Midplane is like a collapsing of the two walls into single layer or a wall, and the thickness attributes elements or thickness attributes given to the elements. Dual domain is we also called as a wrapped element, and that's one of the unique mesh that we create in Moldflow for the quick analysis. And tetrahedral element we also called as a boundary layer mesh. As you can see that we can create all the boundary layer not only at the skin but across the core and to the other side of the skin, and that can be used it for the runners as well. Midplane and dual domain are most commonly used, or I would say now 3D is also commonly used, but if you see like a 10 years back or so, midplane and dual domain was very popular in the automotive and appliance industry. Why is it so? It's very easy to get started. When I say easy to get a dual domain, particularly you import the model with one click, you just create the mesh, fix on the mesh requirements or the challenges and get started with it. This is particularly used for the thin walled parts. Now in quickly definition, what is thin walled part? Any part which is having a thickness in the range of 2.5 to 3 mm, we call as a thin wall part, and above that we consider as a chunky part. And flow width should be at least 4 times the thickness, and we use a Haley-Shaw model to solve it. Now it has some assumptions and drawbacks or shortcomings on it, like gravity effect is ignored, heat conductions is negligible in through the thickness, and so on. You can read on that. How does the calculation of the flow front happen? So it's like dual domain and midplane form the injection nodes, and it grows to the connected nodes. Well, for the 3D, which is very commonly used, and it's been for the new users, they find it very easy to get started. It's particularly designed for the chunkier geometries. Now, what is the chunky geometries? I'll speak on to those in coming slides. It uses the 3D Navier-Stokes equations and solves at each pressure, temperature, and velocity. So a little calculation time is a little higher compared to the midplane and dual domain, but it also takes into consideration like inertia and gravity effect, because these chunkier parts, they are like in hollow, big space, and probably you need to consider those effects or physics. And now each of these mesh has its requirement, but I would say that always try to fix your CAD model correctly. It should not have any open edges or faces, and it should be watertight. Mesh types differs from the model requirement. Like if you're going for the dual domain mesh, it has its different requirement in terms of the orientation or aspect ratio. But for 3D, if you're probably going for and like in dual domain and then going 3D, I would say that fix the dual domain mesh to create the 3D model properly. And midplane, of course, you can create the midplane within the Moldflow, or you can take the help from the third-party solutions which most of the users are trying to get. This is most important where I slide which helps in differentiating the which type of mesh I should go with it. Particularly if you have a geometry, even if it is a thin wall geometry and a lot of features, it's not possible to capture that representation of the top, that is core and cavity, which is needed in the dual domain and midplane as well. Well, if you don't have a parallel walls, you're not able to capture the midplane, and so as in dual domain you're not able to get the mesh match ratio above 80 for the flow analysis and above 90 for the warp analysis. And this could be one of the reasons to go for the 3D mesh, which will help in giving the exact representations to the solver. Again, this is like what is called a chunkier geometry. We call these as a chunkier geometry where the ratio of width to thickness is less than 4:1. And whatever the midplane or dual domain we do, this ratio is in this range or above. So this is one of the important criteria. The reason is dual domain or midplane doesn't do any heat transfer through the thickness phases, which is possible with the 3D mesh. And if you, this was the example, if you try to mesh the two models or the same model with the 3D mesh and dual domain, and you can see the difference in the flow representation. Here the 3D mesh would represent it much better compared to the dual domain mesh, as it is a thicker part. And mesh density, often a question is been asked, what is the exact mesh density? I would say that many times you may need to go with like a couple of density change so that you precisely capture those physics or phenomena. Like one of these cases, like in hesitations, probably if you're going with the coarser mesh, you will not able to capture very precisely that. With the refined mesh, you should be able to capture it precisely. Same is for the weld line. If you don't have the element to represent the weld line where it is needs to be formed, probably you will not get the exact location of the weld line, and sufficient element should be there to represent that weld line. And same is for the A-trap as well. If you don't have an uniform fine mesh, or where the geometries are like in critical, you may not able to capture that exact effect, where like in here in this case it has been captured with an finer mesh compared to the here we have like a coarser mesh. And again the question, what is the exact density? Should I every time go with a higher density mesh? Well, every time if you go with a higher mesh density, probably you will spend a lot of computation time and not necessarily will achieve the accuracy that needed accuracy. And this particular graph shows that the number of elements versus like in the change in the pressure, you will not able to, just increasing the element, it doesn't mean that you are increasing the accuracy. You have to take an proper call. Maybe one or two element change or the global edge length change can help you to reach to the exact required mesh density. I hope this session was helpful for the beginners and it could be a refreshing for the experienced user, and try to implement into the day-to-day simulations. Thank you for your time.